Hi all, today we are going to handle the topic temperature rise in electrical machines. Here you are going to obtain the expression for temperature rise and then you will be obtaining the temperature rise time curve from that expression. Design of heat transfer in electrical machines is as important that of the electromagnetic design in it. Based on the temperature rise in electrical machine, the continuous rating of the machine is determined. What do you mean by a continuous rating of a machine? The constant power at which, in fact it is the maximum constant power at which the machine can run continuously without having a temperature rise above the permissible limits. If the temperature rise is going above the permissible limits, definitely it will affect the insulation and all inside the machine. So it is actually the temperature rise in electrical machines which is determining the maximum power at which this machine can be run continuously. So now you can understand the significance of temperature rise in electrical machines. In fact, it is this temperature rise in electrical machines which is determining the power of the electrical machines. In fact, power rating of the electrical machines. You have seen in your machines lab, each and every machine will be having a maximum power rating. If you are loading that particular machine above that power rating, you won't be able to run the machine continuously. If you are running a machine above its power rating continuously, then definitely this machine's temperature will go or temperature will rise beyond the limits and it will cause or it will damage the machine. So in order to avoid that, you must run the machine continuously only at its rated power conditions. So now you have understood the significance of temperature rise in electrical machines. In order to obtain the expression for temperature rise, certain assumptions are there. Let's look into the assumptions. First assumption is the total losses remains the same and even the machine is considered to be homogeneous body. Homogeneous body means at each and every part of the machine the temperature remains the same. That is what being considered here. All the points at which heat is generated have the same temperature. Even though in actual practice it is not like that, but we are making an assumption that all the points at which heat is generated have the same temperature. Next major assumption is the dissipation of heat energy from its surface is directly proportional to the temperature difference between the hot part and the cooling medium. Third assumption is the temperature of the cooling medium remains constant. You must be aware about all these assumptions, then only you will be able to obtain the derivation of temperature rise expression. Let's look into the temperature rise expression derivation. First, you must be aware about certain notations, in fact certain indications. It is being indicated here on the left side of this dotted line. So let's first take a look into it, then we will move to the derivation part. G indicates the weight of active part of machine. Capital Q, it indicates the power loss or heat developed. You must be aware about the units also. If you know these units, then you will never make a mistake in the derivation as well as in the problems related with this. Next notation is H, which indicates the specific heat. You are aware about the unit of specific heat, joule per kilogram degree Celsius. You also know the expression and the definition of specific heat. That is the amount of heat energy required to increase the temperature of unit mass by unit degree Celsius. Next is S, which indicates the cooling surface area in meter square. There is actually area also here. Then only it comes in meter square. So S indicates the cooling surface area in meter square. Next is lambda. It indicates specific heat dissipation and its unit is watts per meter square degree Celsius. Next is C, which is cooling coefficient, and it's the inverse of specific heat dissipation. So the unit also will be inverse of lambda. Okay. Next, theta. Theta indicates temperature rise at any time t. Please don't get confused. This is indicating the temperature rise at any time t. Theta m indicates final steady temperature rise while heating. Theta n is similar to that of theta m. Only difference is it indicates the final steady temperature rise while cooling. Theta I is initial temperature rise over ambient medium. Ambient medium is actually the cooling medium which is surrounding the machine. Tau h is equal to heating time constant. Its unit is actually in second, and tau c is cooling time constant. Its unit is in also in second. And then finally we will be indicating the small t, which is time, and its unit is also in seconds. So first we will look into heating of electrical machines. Then in the next class we will look into cooling of electrical machines. Cooling of electrical machines expression is same as that of heating of electrical machines. So if you are thorough with temperature rise of electrical machines in heating, from there you can easily obtain the expression for temperature rise during cooling. So let's look into the derivation in detail. We are considering a very small time dt at a time t from the start condition. Please listen very carefully, then only you will understand it clearly. So we are considering a very small duration of time dt at time t from the start condition, and we are going to write down the expression for heat energy developed during this small duration dt, and that expression is given here as h is equal to q dt. As I have already mentioned, what does q indicates? Q is actually power loss or heat energy developed, and its unit is joules per second. So if you are trying to obtain the expression for heat energy developed, definitely the heat energy developed will be having the unit joule. So if you want to obtain the expression for energy, you have to multiply power with time. So that's what we are doing it here. So for this small duration dt, we will be obtaining the expression for heat energy developed by multiplying q with dt, and we are representing it as equation number 1. During this short period dt, the temperature of the body rises by d theta. So definitely some amount of heat energy will be stored in the body of the machine. So let's obtain the expression for heat energy stored in the body of machine. You have already studied this relation in your school classes. The heat energy stored by a body is given by mc delta theta. You are very familiar with that relation where m represents the mass, c represents specific heat, etc. The same relation we are showing it here also. Heat energy stored is equal to, instead of mc delta theta, we are representing it as g h d theta. Clearly we have already mentioned what does g indicates, what does h indicates, that is specific heat, very much similar to that of c in the relation which you have studied in your school classes. And then d theta, that is actually the temperature rise or change in temperature during the small time period dt. So we have obtained the expression for heat energy developed and heat energy stored in the electrical machine. As the machine is running and during this short time duration dt, definitely the temperature of the surface of machine rises by theta over the ambient medium. I have already mentioned you, ambient medium is actually the cooling medium. In machines which you have seen in your labs, the cooling medium is actually the air surrounding the machine. So definitely while the machine is running, the temperature on the surface of the machine goes above the surface temperature means above the surface temperature means above the temperature of the ambient medium. Ambient medium means above the temperature of the air in the case of the machines which you have seen in your labs. Since the surface temperature is greater than that of the ambient temperature, definitely some amount of heat will be transferring from the machine surface to the ambient medium. As you are already aware, there are different methods of heat transfer: radiation, convection and conduction. In conduction, the heat transfer is by direct contact. In radiation, the heat transfer is through electromagnetic waves. Whereas in convection, the particles which are near to the hot body, when it gets heated up, it becomes lighter, and as it becomes less denser, it moves up, and the more denser particles comes close to the surface, and again it also gets heated and it further moves up. So this is the basic process of heat transfer in convection. You have already studied this all in your school classes. Since as far as electrical machines are concerned, or as far as the expression of temperature rise is concerned, I can say that we are considering a situation. In fact, not we are considering the situation. In fact, majority of the heat transfer from the surface to the ambient medium, we can say it also as heat dissipation. So majority of the heat dissipation is taking place by convection. So we don't have to consider the relation of radiation and conduction. We just have to bother only about the heat dissipation by convection. So we will be obtaining the expression for heat dissipation by convection here. So the heat dissipated will be given by lambda S theta dt. As I have already mentioned, lambda indicates the specific heat dissipation in watts per meter square degree Celsius. So if you are multiplying lambda with S and theta, S is actually the surface area in meter square and theta is degree Celsius. So if you multiply lambda with S and theta, then you will be obtaining the relation in watts, and if you are multiplying that watts, in fact what I mean to say is the unit of this term will be watts, and if you multiply it with dt, definitely watts into time is joules. So you will be getting the you will be getting the relation for heat energy dissipated. So we have obtained three relations. One is the heat energy which is developed in the machine, and second is the heat energy which is being stored in the machine, and the third is the heat energy which is being dissipated from the machine. Now we are going to apply the heat balance equation. It is also said to be heat flow equation. So while applying the heat balance equation, we very well know that heat produced will be equal to heat stored plus heat dissipated. We will be substituting the expression of 1, 2 and 3 in this heat balance equation. That is q dt is equal to gh d theta plus lambda s theta dt. Many times it seems to be a common mistake that in the relation for heat dissipation, students forget to mention this dt. So if you are very aware about the unit of this lambda, then you very well know the relation for this heat dissipation or heat energy dissipation. In this left hand side will be having unit joules, so the right hand side also must have the unit joules. So lambda s theta will give the unit watts. So to get joules, definitely you have to multiply it with dt. So take special care about this dt here. Okay, so let's get back to the heat balance relation which we have obtained here, and we are indicating it as equation number 4. From this relation we will be obtaining the expression for dt. dt is equal to gh d theta divided by q minus lambda s theta. Further, we are dividing this numerator and denominator by gh, and then we will be getting the expression like this. In the next step we are going to do integration on this expression. So you are aware about the integration relation. If you integrate 1 by 1 plus ax dx, you will be getting is the answer you will be getting is natural log of 1 plus ax the whole divided by a. In the same way, if you are looking here a is indicated as lambda s by gh. It is actually minus lambda s by gh, and x is theta, so this is dx. So while integrating it, you will be getting natural log of this expression. Along with that, you will be getting the inverse of the coefficient of this theta. So that's what you are getting it here. Inverse of the coefficient of theta is indicated as minus gh by lambda s, natural log of the term in the denominator. Definitely there will be a constant as we are doing integration, so this is known as the integral constant. Next we are going to find the value of k. In order to find the value of k, as usual, we are applying the initial condition here. Initial condition is the condition at which the time t is 0. So at time t is 0, the temperature rise over ambient medium is indicated as theta I. We have already mentioned here theta I is actually initial temperature rise over ambient medium. So at time t is equal to 0, theta I is equal to theta I. Now all of you might have a feeling, in fact it's actually a doubt. Initial condition means time t is 0, so the machine will be in starting condition only. So definitely there will not be any temperature rise in the machine, so the machine's temperature will be same as that of its surrounding medium. That is, machine's temperature will be same as that of the ambient medium. Then how you can say that temperature rise at time t is equal to 0 is theta I? It is actually both at time t is equal to 0, the machine is about to start only, so both the machine surface as well as ambient temperature will be having the same temperature. So definitely there will not be any temperature rise at time t is equal to 0. So at time t is equal to 0, theta's value also must be 0, because theta indicates the temperature difference between the machine surface and the ambient medium. At starting condition, this both must be same. That might be the doubt within you. I will explain that in detail. See, there are actually two starting conditions for a machine. One is cold start. Cold start is the condition which I have just mentioned now. In cold start, you are starting the machine for the very first time in a day. So at that particular instant when you are about to start the machine, the surface of the machine will have the same temperature as that of the ambient medium. So there will not be any temperature rise theta I. The value of theta I will be 0. Suppose you are starting the machine for the 10th time or 15th time in a day, and the 14th time you have started it, you made the machine to run, and you have stopped it after say half an hour. So the machine was heated and the surface temperature of the machine is supposed, okay, I will give you with another example. Consider the situation, the ambient temperature is 30 degrees Celsius. Okay, just like what I have told before, you are running the machine for the 15th time in a day. While the machine was running continuously for half an hour for the 14th time, the surface temperature of the machine rises to 40 degrees Celsius. So while continuous running for half an hour, the machine surface temperature has risen by 10 degrees Celsius over its surroundings temperature or over its ambient medium, and you stopped the machine after half an hour of continuous running. Then next you started the machine in the very next minute. So while starting the machine in the very next minute, that is the 31st minute, at that instant the surface temperature is not same as that of the ambient medium. It will be something very much close to 40 degrees, because it might have started reducing gradually from 40 degrees in that 1 minute. So when you try to start the machine at the 31st minute, the initial temperature rise is 9 degrees Celsius over the ambient medium. It's not 0. The initial temperature rise will have a value of 0 only if the machine is starting in cold condition. What is cold condition is already said now. So you must understand the difference between the cold start and the machine starting after some frequent operations. Hopefully you have understood the difference. Let's get back to the derivation. So from this relation 5 we have to find the value of k. In order to find the value of k, we have to use the initial condition. The initial condition is at t is equal to 0, theta is equal to theta I. Here the initial condition which is taken into consideration is not the cold start condition. We will be obtaining a general expression for the temperature rise, and then we will be obtaining the expression for cold start from it. So applying the initial condition here in this expression, you will get it like this: 0 is equal to minus gh by lambda s natural log of q by gh. No difference with this equation 5. Only thing is this t will be substituted as 0 and theta will be substituted as theta I. So from this you will be getting the expression for k, which is indicated as equation 6 here. In the next step we are going to substitute the value of k in this equation 5, and then we are going to simplify it. While substituting the value of k in expression 5 and further simplifying it, you will be getting the expression like this. That is, after substituting this term k here and then taking minus gh by lambda s common from both these terms, you will be getting an expression. The first term will be natural log of this only, and the second term will be minus of, because you have taken minus gh by lambda s in common, so the second term will be minus of natural log of this expression. So you know, natural log of x minus natural log of y, you can write it as natural log of x by y. So you will be getting the expression for t like this. Further simplifying it, you will be able to cancel the term gh both from numerator as well as denominator. Then you will be getting this relation, which we will represent it as equation number 7. In the next step we will consider the machine was running continuously and the surface temperature of the machine has reached to a final level. That is, there won't be any further rise in temperature, which means the temperature over the machine surface has reached its final steady temperature. So this final steady temperature rise over this ambient medium is indicated as theta m here. It happens only after a continuous running for some time, so we will consider this time period as infinity here. So this final temperature rise after infinitive time period can be considered as theta m. Once the machine has come to this final steady temperature rise condition, or final steady temperature rise condition means there won't be any further rise in temperature of the machine. That means from this instant onwards the value of d theta remains to be 0, because there is no change in temperature on the surface of machine. Hence from the relation of heat stored, you know that heat stored is gh d theta. As there is no change in temperature on the surface of the machine, this particular term as a whole will vanish, because d theta will become 0. As there is no change means the term d theta becomes 0. So this whole expression also becomes 0. Now modifying the heat balance equation accordingly, you will be getting the expression q d theta is equal to lambda s theta m dt, because at a final steady temperature condition or at final steady state condition, temperature rise over ambient medium is indicated as theta m. So you will be getting the expression as q dt is equal to lambda s theta m dt. From this you will be able to obtain the expression for final steady state temperature rise over the ambient medium, that is theta m, which is equal to q by s lambda. You must be familiar with this relation, because this relation is required for solving the problem. So theta m, the relation for theta m has been obtained here. Theta m is equal to q by s lambda. Theta m is the final steady temperature rise while heating. There won't be any further temperature rise after this. Now we are going to make this theta m substitution in equation number 7. So before that we will be making a slight modification in equation number 7. From the equation number 7, from the term inside the bracket, we will be taking s lambda common in both numerator as well as denominator. So while taking s lambda common from both numerator as well as denominator, both s lambda terms in numerator and denominator gets cancelled, and the relation will get transformed into q by s lambda minus theta, and in the denominator it becomes q by s lambda minus theta I. So instead of q by s lambda, you will be making a substitution theta m, because from the equation number 8 we know that q by s lambda is the expression for theta m. So instead of q by s lambda in the relation 7, you will be making a substitution theta m. So you will be getting the expression for t is equal to, t is actually the time period, t is equal to minus gh by s lambda, natural log of theta m minus theta divided by theta m minus theta I. So if you are trying to see this term gh by s lambda, you know the units of each term in this. What is the unit of g? It is actually the weight of the machine. What's the unit of specific heat h? What's the unit of surface area meter square? What's the unit of lambda? All this is already told before. So if you are trying to substitute the units of all this, and if you try to simplify the unit of this term, then you will be getting it as second, which represents it as a constant having the unit of time. So it is indicated as a time constant, which is represented as tau h here. So this relation can be modified into t is equal to minus tau h, natural log of theta m minus theta divided by theta m minus theta I, which can be further solved by writing down the equation for theta m minus theta from this relation. So from this relation it's very clear that theta m minus theta divided by theta m minus theta I will be e raised to minus t by tau h. So from this relation we will be writing down the expression for theta. So theta can be written as theta is equal to theta m into 1 minus e raised to minus t by tau h plus theta I e raised to minus t by tau h. So this is the general expression for temperature rise at any time t from the start condition. The starting might be either cold start or it might not be a cold start. So this is the general expression which we are using for the temperature rise at any time t from the start condition. So now we will be obtaining the expression for temperature rise during cold start. I have already explained to you what do you mean by a cold start. Cold start means you are starting the machine for the very first time in a day. So while starting the machine for the very first time in a day, the surface temperature of the machine will be same as that of the ambient temperature. So theta i's value will be 0 because theta I is the term which is indicating the temperature rise during start. So in this expression you will be substituting theta I as 0 and you will be getting the expression for theta is equal to theta m into 1 minus e raised to minus t by tau h. You can indicate as equation number 10. You are going to obtain the temperature rise time curve from this relation. So while obtaining this curve, you will be getting it as exponential in nature. Y-axis indicates the temperature and x-axis will be indicating the time period t. From this temperature rise curve, you can get the definition for a time constant, that is heating time constant. For that you have to substitute for t is equal to tau h. When t becomes tau h, this relation becomes theta is equal to 0.632 theta m. So tau h can be defined as the time taken by the machine while running for its temperature to rise from 0 to 63.2% of the initial 63.2% of the final temperature rise. Hope it's clear for you. It is defined as the time taken by the machine for its temperature rise from 0 to 63.2% of the final temperature rise, and the final temperature rise is indicated as theta m. So you must be thorough with this two relations. In fact, you must by heart these two expressions. That is the expression for temperature rise, the standard expression, which is represented by equation 9 here. That is theta is equal to theta m into 1 minus e raised to minus t by tau h plus theta I e raised to minus t by tau h. You must by heart this relation, and along with that you must know this relation also. That is the final steady temperature rise, equation for final steady temperature rise, that is theta m is equal to q by s lambda. These two expressions you must by heart it, then only you will be able to solve the problems related with this. Hopefully the derivation is very clear for you. If you have any doubt regarding this, you can either leave a message or you can ask during our Google Meet sessions. Okay, thank you.